So next here we're going to talk about freezing point depression, and it's very similar to boiling point elevation. And so what's going to happen is boiling point elevation moves up because liquid is favored. Well, freezing points need to move down so that window of what is a liquid opens up in both directions. And the reason for that isn't molecules being held back like the boiling point, it's that the solutes get in the way. If I need to stack into a crystal, I need to orient a certain way, organize with my neighbors, and we all stack together. We form a nice orderly structure. And the solutes prevent that from happening. I can't get to where I need to be because there's some stupid ion in the way or something like that. And then on top of it, I have to orient a certain way around the ion. Like if I'm water, I've got to, if it's an anion, I've got to put my hydrogens over there. If it's a cation, I got to go the other way. And so I'm not as able to kind of coordinate with my neighbors and form a nice kind of crystal lattice structure that's an organized, repeating thing that you'll learn more about in the next chapter. But essentially, it's just, they just get in the way. Stupid ions, stupid solutes, whatever they are. It could be, sugar or whatever. And this is the process behind how deicers and road salt work. And so deicer is typically actually isopropyl alcohol, like we've been talking about. That will lower the freezing point of a water solution. And, road salt does the same thing. And road salt is really highly specialized. So it's not like sodium chloride. It doesn't break into 2 pieces. It's sometimes a salt that breaks into like 5 or 6. And so we get a nice big fat Van Hoff factor right there. So we get more bang for our buck. We get more per molecule of salt, or per formula unit. And so the formula is very similar. Delta TF is just our change in freezing point. Van Hoff factor, molality, that's all the same as before. So if it's an ion, it falls apart. If it's a covalent compound, you get an I of 1. And then it's a freezing point dependent constant. We have Kf, not Kb. And it just depends on what the solvent is. So again, you just look it up or it's given you in the problem and just be aware. Now, there is one thing I want to point out. There's 2 conventions with Kf. They can report it as a negative number or a positive number. And how it's reported changes how you calculate your new freezing point of the solution. Because remember, the freezing point is going to go downwards. And so if Kf is negative, that means your delta TF is a negative number, and you just want to add it to the original freezing point of your pure solvent. But sometimes it gets reported as a positive number. And your book, as I remember, your book does one and the lab's going to do another. So be aware of that. And so if you have a positive value for Kf given, you have to subtract delta TF. You're going to get a positive number over here, and if you add it, that's going to move our freezing point up, and we want it to go down, so we have to subtract the positive delta TF. So just be aware, I apologize, it's a weird, there's not one set convention for this, so you just have to be situationally aware, and just recognize that your new freezing point should always be lower than your pure solvent freezing point. So just a heads up on that. And again, I'm going to leave the practice problems to the worksheet, and then we're going to have a lab where you work on this a bunch too. So the math is really straightforward. It's just ID your pieces and multiply them together. So the hardest part might be solving molality or something like that.